In the past week and the previous lecture, we have calculated the radiation fields corresponding to electric dipoles. So, P being electric dipole, we had fields calculated for point dipole, and continuing along the same line, we also had fields calculated for thin wire antenna. We want to go beyond this now, and in the present case, we will calculate fields for a magnetic dipole. And we will see that this gives power which is much less than the point electric dipole when we are in non-relativistic regime, or we are talking about which is equivalent, the wavelength being very large compared to the size of the system, or a variation in time of the currents and charges being very, very small. And this is one case where there is no electric charge. And therefore, the only potential that we have is A is the only potential. So, when we calculate A, we get B, E, everything from here. So, let us begin the calculation. We are talking about radiation from an oscillating magnetic dipole. And the way I am going to form it is by taking a small loop of current. There is a current density J in this, and we will take this in the xy plane. So, this is lying in the xy plane. So, that its area is in the z direction, and the magnetic moment m is going to be pi, the radius square, radius we will take to be a square times the current in z direction, and the current is time dependent. We will take this dependence to be harmonic a little later, but right now let us just work it out in general. So, I can write the current density for this as J R T equals I, which is a function of time. It is in the phi direction and it is along this thin wire. So, I can write this J S minus A, delta S minus A and delta Z in the phi direction. We are using cylindrical coordinates. And the corresponding vector potential A r t is going to be mu 0 over 4 pi integral J r prime t retarded divided by r minus r prime dv prime. Again, j dv prime can be replaced by I times the integral over the length of the coil, and therefore, I can write this as mu 0 over 4 pi I t retarded. It is in the phi prime direction, a d phi prime divided by r minus s prime. That is going to be the integral. Now, again, since we are calculating at retarded time, we have to calculate r minus s prime for the radiation zone. Remember, we are taking a to be much smaller than r, because finally, we want to make this point dipole approximation. So, modulus r minus s prime is going to be equal to square root of r square plus s prime square minus 2 s prime r cosine of angle between r and s. So, we are calculating a r t, which is mu 0 over 4 pi integral I t retarded phi prime a d phi prime over r minus s prime, where we have taken loop to be in the x y plane, current flowing in the phi direction, its radius is a, and we are calculating the vector potential at some distance r. So, we have just written that modulus r minus s prime is going to be equal to square root of r square plus s prime square minus 2 s prime r cosine of gamma, where cosine of gamma is the angle between r and s. You can also write this as angle between r unit vector and s prime unit vector. And this approximately, because s prime is much smaller than r, is given as r minus s prime cosine of gamma. And I will leave it for you to work it out, that cosine of gamma comes out to be sin theta cosine of phi minus phi prime. Where all these phi, theta and all that have their standard meaning. And therefore, t retarded, which is t minus modulus r minus s prime over c, is going to be approximately equal to t minus r over c plus s prime sin theta cosine of phi minus phi prime over c. And remember, where is this s prime? S prime is equal to a, because the current is flowing in the loop of radius a. This you could have written right in the beginning also, because remember, when we had this integral j r prime t retarded dv prime, this had a delta s minus a delta z prime. So, z prime is 0 and s prime everywhere is a. And therefore, the integral can now be written as a r t is equal to mu naught over 4 pi integral I t minus r over c plus a over c sin theta cosine of phi minus phi prime, that I at that time, times phi unit vector prime, a comes out, d phi prime divided by r minus a sin theta cosine of phi minus phi prime. That is the integral that we got to calculate. Again, I am interested in calculating this up to order 1 over r. So, let me rewrite this. I get a r t is equal to mu naught a over 4 pi integral I at t minus r over c plus a over c sin theta cosine phi minus phi prime times phi prime unit vector d phi prime divided by r minus a sin theta cosine phi minus phi prime. Expand this term 1 over r minus a sin theta cos phi minus phi prime using binomial theorem, and this comes out to be 1 over r plus a over r square sin theta cos phi minus phi prime. And since this term second term is r square order, I am going to neglect it, and therefore, I can write a r t as equal to mu naught a over 4 pi integral I at t minus r over c plus I dot at t minus r over c a over c sin theta cosine phi minus phi prime divided by r, and there is a phi prime somewhere, and all this I have times phi prime unit vector and integrated over d phi prime. So, I have two terms, the first term which is pure I and the second term which has I dot. Let us look at the first term. So, first term gives me mu naught a over 4 pi r I t minus r over c integral phi unit vector prime d phi prime, and phi unit vector prime d phi prime integrated over the loop is 0. So, first term is 0. I am left with only the second term. So, my vector potential A r t therefore, now is mu naught a over 4 pi times a sin theta over c I dot t minus r over c. All these are constants, they do not depend on phi prime, and there is a 1 over r. I have collected all these terms times the integral cosine of phi minus phi prime phi unit vector prime d phi prime. Let us focus on this integral. This integral is cosine phi cosine phi prime minus sine phi prime times phi prime unit vector is minus sine phi prime in the x direction plus cosine phi prime in the y direction d phi prime 0 to 2 pi, and this comes out to be unit vector phi itself, because the integral of cosine phi prime sin phi prime is 0 and cosine phi prime square integral is pi. So, there should be a pi also somewhere, pi phi unit vector, and therefore, A R t is equal to mu naught over 4 pi A square I dot calculated at t minus r over c divided by r c sin theta in the phi unit vector direction. We have gotten our A. Now, the magnetic moment A m is equal to pi A square I in the z direction. So, m dot at t minus r by c is going to be pi A square I dot calculated at the time t minus r by c in the z direction, and I have A r t is equal to mu naught over 4 pi A square I dot t minus r over c over r c sin theta phi. So, let me make this picture again. When I go to distance at vector r, m is in this direction shown in the z direction, and phi is like this. A is in phi direction and there is a sin theta. The angle here is theta. So, you can easily see phi is in the direction perpendicular to m and r plane. So, you can easily see that sin theta phi unit vector is equal to z cross r, and therefore, I can write the vector potential A r t in coordinate free expression as mu 0 over 4 pi r c m dot calculated at t minus r over c cross r. That is the answer. And as I had remarked earlier, J is equal to I t delta s minus a delta z in the phi direction. Therefore, divergence of J is equal to 0, and this implies rho is 0. There is no charge, only current, and therefore, phi r t is 0. Only thing we have is the vector potential, and I can calculate everything from that. Let us do that calculation now. So, just to recap, if I have a dipole, a point dipole m pointing in some direction, this is m, and I want to calculate the vector potential at vector r. This is point dipole because we have taken A to be much smaller than r, and pi A square I to be m magnitude. then the vector potential A r t is equal to mu 0 over 4 pi c m dot t minus r over c divided by r cross r unit vector. And from this, I can calculate B as curl of A and E, which is minus d A dt minus grad phi, as only minus d A dt, since grad phi is 0, phi is 0. So, it is easier to calculate E in this case, and I get this to be E equals mu 0 over 4 pi c 1 over r. The only time derivative occurs in m, and therefore, I can write this as m double dot t minus r over c cross r. If m is taken to be m in the z direction, then m cross z will come out to be m in the phi direction times sine of theta, and therefore, in that case electric field E would come out to be mu naught over 4 pi c m double dot t minus r over c over r sine theta in the phi direction. This is my answer for the electric field from a dipole formed by a time dependent current. Let us take a special case. I equals some I 0 cosine of omega t. In that case, this is an oscillating current, an oscillating dipole. E would come out to be mu 0 over 4 pi c omega square with a minus sign I 0 times cosine of omega t minus r over c divided by r sine of theta in phi direction. I think I have missed a minus sign somewhere. So, there should be a minus sign here, there should be a minus sign here, and this will come out to be plus. Okay. So, if I have this small current loop with area in the z direction, with current I being I 0 cosine omega t, at far distance r I have the electric field E equals mu naught omega square m 0 divided by 4 pi c sine theta over r cosine of omega t minus r over c, and it is in the phi direction, where m 0 is equal to pi a square I 0. I may have missed it in the previous formula. Once I have gotten E, I can calculate B also from this, because this is the radiation field. B is going to be 1 over c r cross E, and this is going to come out to be minus mu naught omega square m naught over 4 pi c square sine theta over r cosine omega t minus r over c is in the minus theta direction. So, let us see what is happening. Here is this point dipole. Far away from it at vector r, I have E field which is going in, I have B field which is going in the minus theta direction, and this whole radiation is going out like this. You can calculate the S vector also, the Poynting vector, to calculate the power radiated, which is equal to 1 over mu 0 E cross B, and for radiation this is also equal to 1/2 epsilon 0 E square times C, and it is going in R direction. This comes out to be equal to mu 0 omega raised to 4 m 0 square divided by 32 pi square C cubed sin square theta over R square. And the total power will be integrated of this over d omega, and that comes out to be mu naught omega raised to 4 m 0 square over 12 pi C cubed. So, let us now compare this and the electric dipole. We had earlier studied electric dipole P, which was P naught cosine omega t oscillating back and forth. In this case, the total power radiated was equal to omega raised to 4 P 0 square over 12 pi epsilon 0 C cubed. And now we have studied this m, which is m 0 cosine of omega t, a magnetic dipole oscillating, and in this case the power radiated comes out to be mu 0 omega raised to 4 m naught square over 12 pi C cubed. The two are different. You can see that power magnetic dipole divided by power electric dipole comes out to be mu 0 epsilon 0 m 0 over p 0 square, which is equal to m 0 over p 0 c square. Let us see how do they compare. So, let us compare them. See, suppose I have the length scale L for the dipoles. What that means is, suppose I have this charge, it will be oscillating back and forth up to L. And let us have the time scale T. That means it will be oscillating back and forth in time T. Then P naught is going to be of the order of Q L if the charge is Q. On the other hand, m naught is I, the current, times L square. So, this is going to be of the order of Q over T L square, and therefore, m naught over P naught is going to be Q L square over T times Q L of the order of L over T. So, power magnetic divided by power electrical is going to be L over C T whole square. We find that if we have an electric dipole P naught cosine omega t, and we have a magnetic dipole m naught cosine of omega t, then the ratio of the power from magnetic dipole to power from electric dipole is of the order of L over C t whole square. I can express it in two ways. L over t is like the velocity, so V over C square, or I can also use that C t is lambda, so L over lambda whole square. So, as long as V is much less than C, non-relativistic motion, or L is much less than lambda, system much smaller than the wavelength, power from magnetic dipole is going to be much smaller than power than electrical dipole. If these two become comparable, then these two powers would be comparable. So, let me conclude this lecture by writing that we took a small current loop as a point magnetic dipole. Two, calculated the vector potential and the corresponding fields for it. And 3, calculated the power coming out of an oscillating magnetic dipole. And compare it with that coming from electric dipole. Thank you.